theorem about splitting spheres in S4. Oh, yeah. Is that better? Okay. Yeah, okay. Hi. Yeah, so I wanted to talk about a theorem about splitting spheres in S4. So if you haven't seen it before, I'll first review what a splitting sphere is. So if you have a two-component split link in Sn, so here K1 and K2 are connected, closed, codimension 2, submanifolds in Sn, and they're unlinked. Then a splitting sphere for this link is an Sn minus 1 embedded in Sn, such that K1 lies in one connected component of Sn minus 1, and K2 lies in the other. And so here's a picture of a splitting sphere in S3. So here my link is just this two-component unlink, and my splitting sphere is this pink S2. And you can study splitting spheres up to isotopy. So two splitting spheres are isotopic if there's some isotopy between them that fixes the link. So equivalently, if they're isotopic in the complement of the neighborhood of the link. So the theorem I want to talk about today is about splitting spheres for two unknotted, unlinked S2s and S4. So it turns out that there's infinitely many pairwise non-isotopic splitting spheres for this link. And maybe I'll give some context about the problem. So this answered a question asked by Mark Hughes, Sungwon Kim, and Maggie Miller in 2023. They showed that there exist pairs of non-isotopic splitting spheres for higher genus unlinks in S4. So here, sigma G and sigma H are unknotted surfaces in S4. And the genus conditions are written there. And so their methods sort of required the extra genus. And so they asked if the same thing was true for, I guess, the simplest unlink, which was the unlink of two spheres. And their result and this result also highlights some maybe interesting differences between one-knot and two-knot theory. So in S3, it turns out that any two splitting spheres for a link are isotopic. And this is a proof of that fact. So you have your innermost disk arguments to make the spheres disjoint, and then you have Schoenflies to tell you that there's an isotopy between them. Okay, so that's the theorem. Yes? Oh, everything is smooth. Yeah, let's say smooth. Yeah, thank you. Okay, so yeah, so the proof of this relies on these barbell diffeomorphisms as a main tool, so I'll tell you what those are. So these guys were introduced by Ryan Bundy and Dave Gabay in 2019. They used them to study diffeomorphisms of S1 cross B3. And what they are is just a nice way to construct explicit diffeomorphisms of your four-manifold X. So the way you get these is a three-step process. So first, you write down a nice diffeomorphism of this simple handle body, so S2 cross D2, boundary sum S2 cross D2. And that diffeomorphism will be identity on the boundary. Then you embed this guy into your four-manifold. And then you just push forward the diffeomorphism from step one. So that's a barbell diffeomorphism. So I'll tell you what these steps are. So before I describe the diffeomorphism of the S2 cross D2, boundary sum S2 cross D2, I think it would be nice to start with a two-dimensional warm-up. So now let's consider S1 cross D1, boundary sum S1 cross D1. So we just subtracted one. And this is the picture of that guy. This is the same thing as a twice-punctured disk. And so how are we going to get a diffeomorphism of this? Well, we'll start with a disk, and we'll start with 2 points in our disk, and we'll do some isotopy of them. And we'll use ambient isotopy extension to get a diffeomorphism. So what's the isotopy? I'm just going to put my finger on the pink point and drag it around the green. So maybe it looks something like this. By ambient isotopy extension, I can realize this by a family of diffeomorphisms. So now I have a one-parameter family of diffeomorphisms of D2, and maybe those look something like this. And So the time 1 map of that isotopy extension is now a diffeomorphism of D2 that fixes these 2 points. And its identity on the boundary also. And so I can just cut out those 2 points and get a diffeomorphism of a twice punctured disk, which is identity on the boundary. So that's what I wanted. And one way to see that this is a non-trivial diffeomorphism is by looking at what it does to this blue arc. So you can imagine as I put my finger on this pink point and drag it around the green, this blue arc gets dragged along, and it changes exactly by this sort of thing. And so you can see that it's a non-trivial map on relative first homology. OK, so that's point pushing. I think it's due to Joan Berman. The 4-dimensional version is called arc spinning. So now we're back in S2 cross D2, boundary sum S2 cross D2. So let's maybe view this 4-manifold in a friendlier way. This is just S2 cross I, boundary sum S2 cross I, whole thing cross I, and we'll think of the second interval as time. So here I've drawn 3 time slices of this 4-manifold. And so now you can sort of see that this is just the same thing as B3 minus 2 points cross minus 1, 1. And this is just the same thing as B4 minus 2 arcs, where my arcs are this pink point cross minus 1, 1, and this green point cross minus 1, 1. OK, so I'll play the same game as point pushing. So I'll just write down some isotopy of these arcs in B4 and then extend to get a diffeomorphism. So first I'll draw my arcs a bit differently. Maybe I'll rotate my pink arc, so now it lives entirely in my time 0 B3. By the way, these are B3s, not D2s. So what's the isotopy? Well, I'll just take my pink arc and sweep it around the green point. So that's going to look something like this. I use isotopy extension to get a family of diffeomorphisms. And the time 1 map is now a diffeomorphism of B4 that sends the pink arc to the pink arc and the green arc to the green arc. And so again, I can cut those arcs out. Oh, sorry. So it's identity on a neighborhood of these guys and on the boundary. And so again, I can cut those arcs out and get a diffeomorphism of the manifold I want. And similarly to point pushing, you can see that this is non-trivial by looking, for example, at what it does to this blue D2. So this is a D2 that goes from the boundary of my B4 to a boundary of the neighborhood of my pink arc. And you can imagine that as I grab my pink arc and sweep it around, the blue disk gets dragged along and changes exactly by tubing along this meridional sphere for the green arc. And so it's non-trivial on relative second homology. So yeah, so that's my map of S2 cross D2, boundary sum S2 cross D2. To get a diffeomorphism of my 4-manifold, now all I have to do is specify how I'm embedding this guy. And so we can view this guy in yet another friendly way. So this is just a neighborhood of what's called a barbell. So this is 2 S2s connected by a bar. Fair warning, it's not like Kirby calculus notation. This is like literally just 2 spheres and a bar. The spheres are sometimes called the cuffs, and the bar is sometimes called the bar. And so in order to specify the embedding, I just have to draw the barbell inside my 4-manifold. So what does that look like in practice? Here's the barbell diffeomorphisms that Bunny Gabai constructed of S1 cross B3. So they view S1 cross B3 as S1 cross D2 cross minus 1, 1. So 1-parameter family of solid tori. And they draw their barbell in the time 0 slice. So this is a solid torus. It's a 3-dimensional slice of my S1 cross B3. And this is what the barbell is going to look like. So we start with the left cuff. That's an S2, but it's going to intersect this time slice in an S1 in an equator. And then we start to draw the bar. So the bar is just going to wind k times around the S1 direction. And then the right cuff is just going to appear also as an equator in this time slice. And you can see that the cuffs and the bar are linked in this way. So this guy is delta 5 because we've gone 5 times around, but in general they have delta k. And the barbell diffeomorphism is just supported in a small neighborhood of this barbell. Okay, so what they showed in their paper is that as long as k is greater than or equal to 4, these diffeomorphisms are non-trivial, and in fact, they're non-trivial in a stronger way. So they're not isotopic to the identity mod B4. So what that means is that you can't isotope these delta k's rel boundary so that they're supported in a B4 inside your 4 manifold. Sort of morally, what this condition is saying is that these delta k's are actually diffeomorphisms of S1 cross B3. They don't just come from like plugging in some diff of B4 in some corner of your manifold. But this sort of like mod B4 situation is, we'll use that sort of crucially in the proof. And in fact, they showed that sort of any composition of these delta k's or their inverses is non-trivial mod B4. So that was super cool. And yeah, and now we sort of have all the tools we need to prove the theorem. So this is what we're trying to prove. Oh, by the way, if you have questions at any point, you can stop me. Oh, yeah. So this is specifically for S1 cross B3. Yeah, these diffeomorphisms. Yeah. Yes, yeah. Then you just have, I guess the hard part is showing it's non-trivial, but yeah. Mm-hmm. So I think so they use some invariant to distinguish these diffeomorphisms, and it just vanishes for k less than 4. Yeah. Okay, cool. So great. So now we're ready to prove our theorem. So we want to find splitting spheres. That means we want to find non-isotopic S3s in a complement of 2 unknotted, unlinked S2s and S4. And that guy is just S1 cross B3 connects some S1 cross B3. And so inside this 4 manifold, we have a nice S3 sitting in the middle, which is just the S3 we identify in the connexum. So we'll call that sigma. And so the proof is going to go like this. So first we'll write down some barbell diffeomorphisms of S1 cross B3 connects some S1 cross B3. And then we'll show that they not sigma. Okay, so step 1 is to draw our barbells. So actually, we first have to draw our manifold. So we'll think of S1 cross B3 connects some S1 cross B3 as 2 copies of S1 cross B3, call them L and R, that are sitting side by side. And then we just gouge out a B4 and identify the boundaries. So this is like a 3-dimensional time slice. These pink S2s are like equatorial S2s of sigma, and they're identified. And the barbell that we'll use is sort of, it's just going to look exactly like the delta k's of bunny goodbye, but we'll just string them along through the connect sum. So we start with the cuff. This is an S2 that intersects here in a S1. We'll start winding our bar around. So the bar is going to go once around L. It's going to hit the connect sum sphere, and then it's going to dip into R and go around once. And then it'll just do that k times. And then finally, the right cuff will just link the bar like that. Okay, so this is, oh yeah. Yes, yeah, so see, these are identified, yeah. It's like some slice of my S3, yeah. Okay, so this guy is beta 5, because we've gone around 5 times, but in general, there's beta k. Okay, so this is our barbell. And so now we want to show that our barbell actually knots sigma. So for a contradiction, let's suppose that it doesn't. Let's suppose that beta k of sigma is isotopic to sigma. Okay, that means after isotopy, we can assume that beta k of sigma is equal to sigma. Is that wise? And of course, that means that beta k restricts to a diffeomorphism of S3. And then there's this nice theorem of Cerf that any orientation-preserving diffeomorphism of S3 is isotopic to the identity. And so that tells us that beta k restricted to sigma is isotopic to the identity. And that tells us that our barbell is isotopic to a diffeomorphism, which is the identity on the boundary still, and also identity on a neighborhood of our connect sum sphere, sigma. And that diffeomorphism will actually split into two diffeomorphisms, one of the left S1 cross B3 and one of the right S1 cross B3. So these FL and FRs are diffeomorphisms of a punctured S1 cross B3 that's identity on the boundaries. So that's like a cartoon of those. Okay, so now this is where we are in the proof. So we have our barbell on the left and our FL-FR business on the right, and we have that they're isotopic. So to get a contradiction, now we just want to show that they're not isotopic. And how do we do that? So first, we'll make some nice observations. So the boundary of L connects some R is going to be two disjoint S1 cross S2s. And so if we cap off the right one with a D2 cross S2, that gives us L connects some S4, which of course is just S1 cross B3. Okay, so let's play this game and see what it tells us about our diffeomorphisms. So we start with beta K, our barbell. This is the diff of L connects some R, which is identity on the boundary. We cap off R with an S2 cross D2 and extend beta by the identity. So now we have some diffeomorphism of S1 cross B3, call it beta K hat. And now you can see that you can just kind of take these strands on the right and push them back into L. And so this is going to be isotopic to the delta K's constructed by Bunny goodbye. So that tells us that this beta K hat is non-trivial mod B4. And that in turn tells us that our original barbell is a non-trivial diffeomorphism, mod B4. Because if it were trivial, then we could just do the whole isotopy inside L connects some R. Okay, so great. So our barbell is actually non-trivial. That's good. This actually tells us the exact same information about FL, FR. So if we just play the same game, we extend by the identity. Now we have some diffeomorphism FL, FR hat of S1 cross B3, which is non-trivial mod B4. And this actually tells us something nice about our purple diffeomorphism FL. So you'll recall that FL was a diffeomorphism of a punctured S1 cross B3. So we can just plug the 4-ball back in and extend by the identity. Now we have some diffeomorphism FL hat of S1 cross B3. And this guy is equal to FL, FR hat outside of a B4. So FL hat is also non-trivial mod B4. Yeah. Were there questions, or was that fast? Or? Okay, cool. Great. So now we're in a good place to get a contradiction. So remember, we had our barbell on the left and FL, FR on the right. We want to show they're non-isotopic, and now we also know that this purple diffeomorphism is non-trivial mod B4. Okay, so how do we distinguish these maps? So we'll distinguish their lifts in a cyclic cover. So let's consider the k-fold cyclic cover of L connects some R, where we just unwind R a little bit. So this is a two-dimensional like analog of that. Here I have S1 cross B1s playing the role of my S1 cross B3s. And the cover is going to be some connect sum of k plus 1 S1 cross B3s, where you have one long S1 cross B3, R tilde that covers R, and then like k orbiting S1 cross B3s that cover L. And so let's see what our lifts look like in this cover. So this is our barbell in the base. This is beta 5. So there's one barbell in the base. So it's going to lift to k disjoint barbells in the cover. And one of those lifts is going to look like this. So we start with a cuff in one lift of L. We go around L once until we hit the connect sum. Then we dip into R tilde, and we go around one click. And then we dip into the next lift of L, and so on and so on and so on. And so what the barbell does in the cover is it unwinds. And so now it's no longer looped around any S1 factors. It no longer links itself. And so you can see that you can just sort of pull this barbell to live inside of a little 4-ball inside the cover. So the lift of our diffeomorphism beta K is just going to be some composition of barbells that look like this. And so the lift beta K tilde is going to be trivial mod B4. Okay, so what about FL, FR? So here's FL, FR. The lift is going to look like this. So on R tilde, we have some lift of FR, and on the orbiting Ls, we just have like exactly the same diffeomorphism, FL. And so we want to show that this lift is non-trivial, mod B4. OK, so to do that, we can just play the same game as we did. So this is some connect sum of S1 cross B3s. So we can cap off like all but one of them with D2 cross S2. So let's cap off R tilde and then like 4 copies of L. We do that, we extend our diffeomorphism by the identity, and now we get a diffeomorphism of S1 cross B3 connects them S4. And now all this sort of junk, this blue stuff and these 4 purple things are all contained inside of a B4, now an S1 cross B3. And so this diffeomorphism is going to be equal to our purple guy, FL hat, outside of a B4. And since our purple guy was non-trivial mod B4, that means this extension is non-trivial mod B4. And that means that the original lift is non-trivial mod B4. And that means that the lifts of our 2 diffeomorphisms are non-isotopic. And of course, that means that the original diffeomorphisms are non-isotopic. So that gives us our contradiction, and that proves the theorem. And yeah, and to get like infinitely many splitting spheres, you just repeat the same argument using like beta k, beta j inverse. OK, how am I? Oh, great. OK, are there questions, or this is like a good time to stop for questions? But if there's no questions, then that's fine too. Yeah, I know it was a bit fast, but OK. So do I have till 11? Or oh, OK. Yeah, OK, great. So yeah, so maybe in the last few minutes, I just wanted to mention some other cool things that you can prove using barbells. So this is joint work in progress with Gi-hyun Nam and Sungwon Kim, who are both in the audience. Shout out, Gi-hyun, Sungwon. So the first thing that you can do is you can just get like a lot more splitting spheres. So the Hueskin-Miller paper on splitting spheres sort of provided these examples of non-isotopic splitting spheres for some cases of unlinks of surfaces. The theorem we just showed proved it for S2s and S4. And so in general, we can get splitting spheres for any combination of any genus unlinks. And we can also get them for smaller submanifolds. So if you have just even 2 circles sitting in S4, then there's infinitely many S3s that split them, and like various other combinations. The second thing is a theorem about knotted handle bodies. So we can show that there exist infinitely many pairwise non-isotopic 3-dimensional handle bodies of any genus in S4. Here the isotopies are all rel boundary, so they fix the surface. And the handle bodies have the same compressing curves, so the same curves on the surface bound disks inside the handle body. Yeah, so maybe just to state some context on this result. So the paper in which Bunny Gabai introduced these barbell diffeomorphisms, in that paper, they actually showed that there exist infinitely many knotted 3 balls in S4, so like genus 0 handle bodies. So here the isotopies are fixing the S2. That was important. And in that paper, they conjectured that the same thing would be true for higher genus handle bodies. And so in 2019, Mark Hughes, Sungwon Kim, and Maggie Miller showed that it was true for handle bodies of genus bigger than or equal to 2. And the methods that they used were sort of similar to the methods they used to show the result on splitting spheres. And in particular, it required this sort of higher genus condition. And so the solid torus case was open. And so using barbells, we can sort of show that last remaining case. And it's sort of general enough that it extends to any genus greater than or equal to 1. And there's actually some interesting like 5-dimensional phenomenon that occurs here. So the knotted 3 balls that Bunny Gabai constructed, they live in S4, but if you push their interiors into B5, they become all isotopic to one another, rel boundary. And in fact, Daniel Hartman showed that if you have any two B3s in S4 with the same boundary, you push their interiors into B5, then those push-ins are isotopic. So there's no sort of five-dimensional knotting of B3s. On the other hand, in Hueskin-Miller, they showed that their handle bodies remained knotted in B5. And our handle bodies also have this property. So sort of the five-dimensional knotting is maybe like differs between the genus 0 and genus non-zero case, which is maybe cool. In fact, we can show that by showing something stronger. So if we take two of our knotted handle bodies in S4, so like a horizontal one and a vertical one, and we push their interiors into like the south and the north B5 of S5, then those glue up to be an S3 and S5, and we can actually show that those S3s are knotted. So in particular, these S3s have, because they're built from two solid tori, they have 4 critical points with respect to the standard height function on S5. And so they're sort of like as simple as they can be from a Morse theory standpoint, but still knotted. And maybe I'll mention that the analogous statement in S4 is false. So Charlemagne showed that if you have an S2 and S4 that has 4 critical points, then it's always unknotted. Yeah, so maybe I'll end there. I think that's all I wanted to say, but yeah, thank you.
If you can go okay, stop here. So you mentioned that one of the barbells unwinds in the cyclic cover.
Oh, yes.
And then you can isotope it and it's 4 ball
yes.
Localize the diffeomorphism. When you isotope it, don't you track the other?
Yeah, that's a good question. Yeah, so so the lists are going to be linked, actually. But the thing is there's no self-linking of the barbells. And so like as diffeomorphisms, these diffeomorphisms have disjoint supports and disjoint like ranges, I guess. And so they all commute with each other. Maybe that's actually not what I wanted to say. The main thing is like the lift of beta k is going to be a composition of barbells that look like this. And each barbell that looks like this is individually like trivial. And so like beta k tilde is going to be like beta 1 tilde composed with beta 2 tilde composed, oh, that's bad indexing. But each of the beta I tildes are going to be trivial. So the whole thing is going to be trivial. Yeah, that's a good question. Thanks. Mm-hmm. Oh, sorry. Sorry. Oh, that's a good question. So in this last slide, this other combinations thing, it refers to, so I think if you have a genus G greater than or equal to 1 unknot and unknotted surface and like anything on the left, then we can show that. But yeah, I don't think we quite have like anything and anything. Yeah.
The cyclic covers and then sort of fitting bits in is a bit like taking a branch cover.
Yes. Yeah.
Because you're starting from scratch with these unknotted 2 spheres unlinked, and you just took a branch double cover of S4 and a branch over those 2 spheres.
Yeah.
You'd have S1 and I think S1 times S3, fingers crossed. I wonder whether your splitting spheres would lift to exotic, non-standard 3 spheres.
Oh.
S1 times S3.
Yeah, that's a good. I haven't thought about that. Yeah, that could be interesting. Yeah.
What happens to the barbells?
Yeah, it would probably be. Yeah, that would be an interesting thing to think about. Yeah, I guess the nice thing about, or one of the nice things about barbells is like, it's sort of like very easy to study their lifts, like so you can just draw them, and yeah, so yeah, that'd be cool. Oh, thank you so much.